This presentation will introduce the idea of hypothesis testing and outline the steps involved. Hypothesis testing differs from the confidence intervals addressed earlier in the course, where we wanted to estimate an average or proportion and its levels of uncertainty or margin of error. Here, we will frame each problem as a yes or no question, and we will determine the validity of a statistical claim. As with confidence intervals, detail is very important in hypothesis testing, since our final conclusions are connected to the underlying mathematics and the logic of our process. While confidence intervals are extremely useful in science and understanding, hypothesis tests lend themselves better to decision points where we must choose one of the two alternatives. In this presentation, we will use the following example to discuss the steps involved for hypothesis testing. A bank has set up a customer service goal that the mean waiting time for its customers will be less than 2 minutes. The bank randomly samples 30 customers and finds that the sample mean is 112 seconds. Assuming that the sample is from a normal distribution and the population standard deviation sigma is 28 seconds, can the bank safely conclude the population mean waiting time is less than 2 minutes? As the last sentence indicates, this is a yes or no question. We want to test bank's claim whether their average waiting time is less than 2 minutes. The first step for any hypothesis testing is to set up the question. We do this by creating a null hypothesis, the assumption we are looking to check or disapprove, and its mirror, the alternative hypothesis, which we are looking for evidence to support. The null and alternative hypotheses are two statements that are completely opposite of each other. They are statements about the population parameters, for example, mu and p. The null hypothesis is written as h with a subscript 0. It is an assumption to be challenged. It's usually the status quo or default. In hypothesis testing, we are looking for evidence to disapprove or reject the null, but we can never have enough evidence to prove it or accept it. The null statement always has an equal sign, either alone or as a part of inequality. The alternative is written as HA. It is opposite of H0. It is a new claim that we want to prove. We are looking for evidence to prove the alternative HA, meaning reject the null. HA never has an equal sign. It will have either a less than, a greater than, or a not equal to sign. Between them, the null and alternative are mutually exclusive and exhaustive. One of them must be true, and they can both be true. Here are some examples of H0 and HA. H0 is generally placed on top of HA. Note that all the statements are about population parameters, mu or p, not sample statistics, x bar or p bar. The sign of inequality in the alternative determines the type of test, whether it's a lower-tailed, upper-tailed, or two-tailed test. Let's get back to the bank example and set up the hypothesis for this example. The alternative is usually easier to set up compared to the null, because it involves the research question we want to test. For this example, that is whether the average waiting time, mu, is less than 2 minutes. So HA is mu less than 2 minutes. I change 2 minutes to 120 seconds. Because H0 is the opposite of HA, H0 is mu is greater than or equal to 120 seconds. This is the finalized presentation for step 1. The test we will perform is a lower-tailed test. This can be seen from the sign of inequality in HA. Generally speaking, in step 1 of hypothesis testing, we have decided on two statements about a population parameter. The null is the average waiting time is at least 120 seconds, and the alternative is the waiting time is less than 120 seconds. These two statements are plotted together here. The null is placed to the right of the alternative. In the following steps of hypothesis testing, we will make use of some useful information we get from the data to determine which of the null and alternative is more likely to be true. This useful information is measured in terms of a test statistic in step 2. Step 2 of hypothesis testing is to compute a test statistic, which measures the distance between the null and evidence from the data. For numerical data, hypothesis tests are mostly about population means. The evidence will be sample mean from the data. The test statistic would be either a z-score if the population standard deviation sigma is known, or a t-score if population standard deviation sigma is not known. For categorical data, tests are about population proportions. The evidence is sample proportion, and the test statistic is always a z-score. In example 1, the test statistic is a z-score of a negative 1.565. The negative value of a z-score indicates that our sample mean is less than the null value of 120 seconds. After we calculate the test statistic, a relative distance measure between the evidence and the null, we want to be able to say whether evidence is far enough away from the null to reject the null. There are two different approaches here in step 3. One approach is called the critical value approach, in which we find a cutoff value. If the evidence is further than the cutoff from the null, we would reject the null. The second approach is called the p-value approach, in which we calculate the p-value, which is a probability outside our evidence. If this probability is small, we would also reject the null. Let's start with the critical value approach first. We want to find a critical value that will be determined using a significance level alpha, which is usually specified in the problem. Significance level is actually related with type 1 error that are discussed in other presentations. Once critical value is determined, we will compare this critical value with the test statistic obtained from step 2. For our example, the alpha is given to be 1%. We plot a bell curve with the center being the null value of 120 seconds. Because this is a lower-tailed test, if the evidence from the data lies on the right-hand side of the null value of 120, we do not have evidence to disapprove the null. If the evidence lies on the left-hand side of 120, we have somewhat evidence to reject the null. The critical value is the cutoff value that would allow us sufficient evidence to reject the null for the given level of significance. A 1% significance level represents that the lower-tailed probability to the critical value is 1%. Using the z-table, we find the negative 2.33 has a lower-tailed probability of 1%. Our critical value is negative 2.33. We are done with step 3. It is worth noting that the critical value is a negative score for a lower-tailed test and a positive score for an upper-tailed test. For two-tailed tests, there are two critical values, one positive number and one negative number. The critical values are determined using alpha divided by 2. In step 4 of critical value approach, we will compare the test statistic with the critical value to make a conclusion whether or not to reject the null. Our test statistic is negative 1.565, which is not as far as the critical value to the null, so we do not reject the null at 1% significance level. Therefore, we fail to reject the null for this example. The conclusion we make in hypothesis testing is either to reject the null or not to reject the null. We would not say we have found enough evidence to accept the null because the null can never be really proven. We will now solve the same problem again using the p-value approach. The first two steps are identical. The differences lie in steps 3 and 4. The two approaches always give the same conclusion. In p-value approach, we compute a p-value that is a probability of obtaining our evidence if the null is true. More specifically, p-value is equal to the probability of obtaining a test statistic that is further away from the null than our obtained test statistic from the data. If the p-value is very, very small, that means it is unlikely for us to obtain our test statistic if the null is true. This actually means the null is unlikely to be true and we find evidence to reject the null. Once p-value is determined, we will compare it with alpha. If it is smaller than alpha, we would consider it as being small enough to reject the null. Our test statistic is negative 1.565 as labeled on the diagram below. Test statistics that are further away from the null would be those to the left of the negative 1.565. So the p-value is the lower-tailed probability of negative 1.565. Using the z-table, we find this lower-tailed probability to be 0.0582. Next, we would have to compare the p-value with alpha that is 1%. We reject the null when p-value is smaller than alpha and fail to reject the null otherwise. For this example, p-value is smaller than alpha, we would reject the null at a 1% significance level. Using both critical value approach and the p-value approach, we are able to reject the null. In conclusion, we find enough evidence to claim that the population average waiting time is less than 2 minutes. Here is the summary table for the critical value approach. This is the summary table for the p-value approach. It is important to note that the p-value rejection rule is always the same regardless whether it is a lower tail test, an upper tail test, or a two-tailed test. We reject the null when the p-value is smaller than alpha. In a critical value approach, we compare test statistic with critical value for a particular significance level alpha. In a p-value approach, we compare the p-value associated with the test statistic with the significance level. Although we are comparing different things in these two different approaches, we have been using the same test statistic and the same significance level. It is not surprising the conclusions from these two different approaches are always the same. Either all reject or all fail to reject the null.